Good morning, everyone. Today we will start with the designing of IIR filter by frequency transformation method. Okay. Now, if you look into the frequency transformation method, frequency transformation. We talked about the frequencies in the two domains. First, in the what do you call in the analog domain, and the second in the digital domain. Okay, so we can modulate the frequency response of a filter either in the analog domain or in the frequency domain. Okay, so what happens in the frequency transformation method? So we can apply the frequency transformation method either in the analog frequency domain, which is in the S plane, and our transfer function is given by Hs. On the contrary, we can also do the transformation in the digital frequency domain, where the transfer function of the system is given by Hz. Okay, so if you do the transformation in the Hs domain, so what happens? You will be given with Hs, then you will be transforming it to another domain, say H dash s, and then you will apply transformation, this either bilinear transformation method or impulse invariance method, whatever method you want to apply, you apply to get into the HZ, okay, or the digital domain. Okay, whereas in the second case, if you want to apply the frequency transformation in the digital frequency domain, then initially you will be getting Hs, then you have to apply either bilinear transformation method or impulse invariant method to get into the Hz domain, digital domain, and then you may apply the digital frequency transformation to get Hz, which should be the required transfer function or the filter, or the transfer function of the filter which you want to design. Okay, so due to this reason, if you see, we can either apply this frequency transformation in the in the analog domain or in the digital domain, and ultimately we can get into the to the transfer function of the digital system which we want to design. Hence we will be discussing about both these transformations. Okay, when we talk about frequency transformation, what we usually do is that we perform a frequency shifting of the passband filters. Okay, of a passband filter. So what happens over here is that the frequency shifting can be done in these four processes: low pass filter to low pass filter, low pass filter to band pass filter, low pass filter to high pass filter, and low pass filter to band stop filter. Okay, so in all these transformations, what we are seeing, that the starting frequency response, it is in the it is having the response of low pass filter. Okay, that means when we try to apply a frequency transformation method, we usually start with a low pass filter, and from here we design the other types of filters. Okay, now why this is so? This is because if we use LPF as the starting filter, then what then the designing of the starting filter, it becomes easier. Okay, So whether you talk about analog frequency domain, whether you talk about digital frequency domain. So if the analog frequency domain, if you try to design a low pass filter, this is your S plane, sigma j omega. So you place a pole near to the what you call, near to the real axis or on the real axis. So over here you will be getting a region which is having a low pass filter stop. Okay. In our Butterworth filter designing, we have seen the filter poles. So when we design any filter, the filter poles, they are present as conjugate poles, right? So what does that mean? If you place a filter not on the real axis, if you place a filter on the second quadrant, on the third quadrant there is a conjugate pole over there, and you will be having a composite effect. Now designing this filter, this low pass filter, it is easier because if you see, you will be having something, a composite effect, and it will be having something like this. Now as you try to move this on the positive side or the towards higher frequencies, then the pole moves to the upper side and the lower pole, it moves to the lower side. Okay. So we are basically separating or segregating the frequency responses. Okay. Right. Also, the designing of the other types of filter, it becomes bit difficult. Where to place the poles, where to place the zeros, because if you are talking about band stop filter, you need to put some zeros over there. Okay, so where to place? So the designing criteria, it becomes somewhat difficult. Okay. However, as I showed you in the analog domain, you can design the low pass filter quite easily. The same is the case when you talk about designing of the digital filters. So designing of the digital filters, it happens in the Z plane, real Z, imaginary Z. Okay. So you can place a pole on the real axis. Okay. However, if it is not on the real axis, so when you are placing a pole on the real axis, basically there are two poles actually. Okay. And if you try to segregate that, then what happens? You get a pole in the first quadrant and you get another conjugate pole in the fourth quadrant. Okay. So over here also, if you see, if you just place two poles near to the DC frequency, you are able to design the filter in a easier way. Okay. However, if you want to make the other types of filters, you have to take into consideration other factors like the placement of the zeros and all these things, and where you would place the poles accurately, where you would be placing the poles and all these things. But while you are using this frequency transformation method, and when you design the low pass filters, as we can see, the designing of the low pass filter is quite easy. So our life becomes quite easier. Okay. So we don't have to take care of the many other things uh, which I have just told you to design the more complex filters. Okay. Herein we are just interested in the designing of the low pass filter. Okay. Now why this is important? So let us take the frequency response of a low pass filter. Okay. Now in the digital domain, what happens? Our frequency response is limited to minus pi to pi. Okay. Say for example, I have a low pass filter having filter response in the range of minus pi by 4 to pi by 4. Okay. Now if I have to transform this filter to a band pass filter, what I have told previously, we have already discussed this kind of arrangement. Okay. Now, when you are talking about this kind of arrangement, see, minus pi by 4 to pi by 4. Okay. So here there are two stubs, basically 0 to pi by 4 and 0 to minus pi by 4. So what I have done, I have moved the 0 to pi by 4 factor or the region to pi by 4 to 3 pi by 4. Say I want to design a band pass filter having cutoff frequencies at pi by 4 and 3 pi by 4. Okay. So here I transform it to pi by 4 to 3 pi by 4, and the negative of domain, it is being moved to or pushed to minus pi by 4 to minus of 3 pi by 4. Okay. So how this is possible? This is possible because when you are talking about low pass filters in the digital domain or in the even in the analog domain, we said that the frequency response, it repeats itself. Okay, the frequency response, it repeats itself. Okay. So when it repeats itself, that means in the low pass filter we are having frequency components. Again, after pi, if you go, you will find that pi, then 2 pi, and around the 2 pi region you will be having this response which is getting repeated in itself. Similarly over here also in the negative domain also, if you go towards the negative of 2 pi, you will be getting some response like this, right? So this filter response, it is getting repeated over there also. So another important thing what we discussed is that whatever we design in the positive half, there will be a negative impression in the negative frequency cycle also. So if you look, if I just move this part to a particular position of our need, we will be transforming the negative frequencies also in the negative domain so as to create a negative impression. Okay. Similarly, this is how we get from low pass filter to band pass filter. So it is quite easy, you can see. Now similarly, if I further move these components and I get to the region that this pi by 4, it comes out to 3 pi by 4, then I get a region of 3 pi by 4 to pi, and similarly in the negative region I will get minus 3 pi by 4 to minus of pi. Okay, and this other extra part which I have drawn, it is due to the repetition effect in the digital domain, right? Because after pi and after minus pi, they get repeated itself, right? So what is this? We have already discussed about this. When we try to design any digital filter, we usually consider minus pi to pi region. So if you look into the minus pi to pi region, what filter we have designed? We have designed a high pass filter. We have designed a high pass filter, right? So what we have done? We have designed the low pass filter, and just we are moving these filters accordingly, these passband domains accordingly. So how do we are moving? We move by frequency transformation. Okay, so we apply some frequency transformation method and we shift this frequency ideal frequency not sorry ideal the frequency response components suitably so as to design different types of filters. In the similar way, we can also design the band stop filter. Okay. So this is how the frequency transformation method it works. Okay. Now coming to the analog frequency transformation method, the first one is the low pass filter to low pass filter. So here the S, you will be getting some transfer function in S, right? So in the equation, your S will be replaced with omega p divided by omega dash p multiplied by S. Okay, omega p divided by omega dash p multiplied by S, where omega p is the H frequency of the available filter, and the next one is the H frequency of the filter to be designed. Okay, so if you see over here, I have talked about low pass filter to band pass filter and low pass filter to high pass filter. But what happens to low pass filter to low pass filter? Suppose you are having this minus pi by 4 to pi by 4. Okay, but you need to change the type of the filter when you are type of the low pass filter. So what you want to do over there? Basically, you want to change this frequency components, right? So what to do? You may be interested in designing a filter, say, which is having cutoff frequencies at say minus 3 by 4 to sorry 3 pi by 4, right? So you have designed a filter which is having a cutoff frequency at pi by 4, but now just by implementing this is in the digital domain, but similar thing can be done in the yeah, in your frequency domain also. Okay, so just by applying a simple transformation, you can design another filter which is having characteristics which is altogether different. Okay, it might so happen, say for example, uh, you are working on a on an ECG signal, and you design a filter according to your hardware which has been given to you. Okay, say for example, when you go in another organization and they ask you to to do a similar kind of job, however you find that the hardware, the digitizing devices what you are having is a different specification. Okay, different specification means it works in a different sampling frequency. So what you will do, you already have a program with say low pass filter designed with you, which is suitable to work at a sampling frequency say f dash s, right? Now you have to work on fs. So what you will do? Okay, because everything will change. So then these kind of transformations, they come into the picture, because your sampling frequency will ultimately define these coordinate values. Minus pi by 4, pi by 4. Suppose you want to have something in over there. So what you will do? So when you change the sampling frequency, the frequency component in this at this pi by 4 location or minus pi by 4 location, everything changes, right? So just by applying these transformations, you will be able to save a lot of efforts, right? So here, if you see, we can perform the low pass transformation to the low pass transformation just by replacing the S in the existing Hs with omega p, H frequency of the available filter, divided by omega dash p multiplied by S. Okay, so this is the equation. Now, if you have to convert a low pass filter to a high pass filter in the analog domain, S will be replaced with omega p multiplied by omega dash p divided by S. Okay. Then low pass filter to band pass filter, omega p multiplied by S square plus omega L plus omega u. Omega p is the edge frequency of the available filter. Omega L and omega u are the cutoff frequencies of the band pass filter. Okay, this one divided by S multiplied by omega u minus omega L. Okay, then we can have low pass filter to band stop filter. Over here, omega p, the pass band edge frequency of the available filter, multiplied by S multiplied by omega u minus omega L divided by S square plus omega u multiplied by omega L. Okay, so these are the transformations in the analog domain. Okay, then in the digital frequency transformation, we have this thing, low pass filter to low pass filter. Over there, Z inverse will be replaced with Z inverse minus alpha divided by 1 minus alpha Z inverse, where alpha is given by sine of omega p minus omega dash p divided by 2 divided by sine of omega p plus omega dash p divided by 2. Okay, so you have to apply this transformation and your alpha is given by this one. Okay, then low pass filter to high pass filter, Z inverse to Z inverse plus alpha divided by 1 plus alpha Z inverse, and here alpha is given by cos of omega p plus omega dash p divided by 2 divided by cos of omega p minus of omega dash p divided by 2. Okay, so omega p, it is the, what is omega p? Edge band frequency of the available filter. Omega dash p is the edge band frequency of the filter to be designed in both low pass filter and high pass filter, right? Then low pass filter to band pass filter, Z inverse, it will be given by Z to the power minus 2 plus alpha 1 Z inverse plus alpha 2 divided by alpha 2 Z to the power minus 2 minus of alpha 1 Z inverse plus 1, where alpha 1 is given by 2 alpha k divided by k plus 1 and alpha 2 is given by k minus 1 divided by k plus 1, and here k is given by cot of omega u minus omega L divided by 2 tan of omega p by 2, and alpha is given by cos of omega u plus omega L divided by 2 divided by cos of omega u minus of omega L divided by 2. Okay, so if you see, there is no omega p over here in the alpha, whereas in 1 and 2 you are having omega p also. Here in low pass filter to band pass filter, your omega p is in the k value. Okay, in the previous case there was no k value, so please look look into these equations carefully. Okay, and practice these equations, otherwise you will forget. Then lastly, we have low pass filter to band stop filter. Over here we have Z inverse. It will be transferred to Z to the power minus 2 minus of alpha 1 Z inverse plus alpha 2 divided by alpha 2 Z of minus 2 minus of alpha 1 Z inverse plus 1. Okay, and here in alpha 1 is given by 2 alpha by k plus 1 and alpha 2 is given by 1 minus alpha divided by 1 minus k divided by 1 plus k, and alpha is given by cos of omega u plus omega L divided by 2 and cos of omega u minus omega L divided by 2, and k is given by tan of omega u minus omega L divided by 2 multiplied by tan of omega p by 2. Okay, so these are some of the transformation equations which are used for designing of filter by frequency transformation method. Okay. Now there is another method, the last method. It is the approximation of derivatives. Okay, approximation of derivative method. Okay, so here what happens is that suppose you are given with time axis and amplitude values for any given signal. So you will be having T1, T2, T3, and all of these, the difference between T1 and T2 is equisampled. Then T2 and T3, it is having same value as that of T1 and T2, and so on, it goes on. Then correspondingly you get values of x1, x2, x3. So when you talk about differentiation, what you do, say dy by dt, if you have to find out, so what do you do basically? So it is basically x2 minus x1 divided by t2 minus t1, right? However, in the case of digital signals, t2 minus t1, then it is equal to t3 minus t1, sorry, t3 minus t2, this is equal to t4 minus t3, which is equal to capital T, which is the which is equals to 1 by fs, time, what do you call, um, time period of the sampled signal, right? And it is given by 1 by fs, and for a digital signal fs is constant, so everywhere you have these values. Now what happens to the y values? This is present value minus the previous value. Okay, present value minus the previous value. Okay, so x2 minus x1. So this equation, what I have told, it is regarded as backward differentiation method. It is regarded as backward differentiation method. The derivatives can also be conducted by using forward difference method, where you will be getting x1 minus x2 divided by capital T. Okay. However, in this case, your x1 will be the present value. Whatever is your start value is the present value. So x1 will be your present value, and x2 it becomes the future value. x2 it becomes the future value. But from our what do you call, from our study we know that uh, it is not possible to realize filters which needs future values, because how will you get the future values? It is not possible to get the future values um, uh, from many of the systems. It may be possible in many of the other fields, but in biomedical signal processing, when you are talking about the present value, you don't know what will happen in the future. Okay, say for example, if you want to predict, if you want to, if you are recording ECG signal, you don't know what will be the value of the next instance. If the patient goes into, say, he's having a normal heart rate, and then suddenly he gets tachycardia, then his heart rate profile will change. So you don't know the future values. So the forward differentiation method, it is of no use in biomedical signal processing. Okay. So we will stick to backward differentiation method. Okay. Because it only takes the present input and the past input. Okay. So from here we get dy by dt, it is equal to y of nt minus y of nt minus capital T. So we get from here y of n minus of y of n minus 1 divided by capital T. Okay, and this is equal to the Hs. Now if I apply Z transform over here, then it becomes Hz equals to 1 minus Z inverse divided by T. Okay. So that means if we compare Hz and Hs, we say that S is replaced with 1 minus Z inverse divided by T. Okay. S is transformed or it is replaced with 1 minus Z inverse divided by T to design a filter by approximation of derivatives. And this is true only for backwards difference method. Okay. Whenever I will be giving you a question, if I mention that it is just like in the next example, we will see I have given you convert bandpass filter, analog bandpass filter to a digital filter by backward difference derivative method. If this is not given, then you have to write that I am applying backward difference derivative method to transform this filter into the digital domain. I may give that convert an analog bandpass filter to a digital filter by approximation of derivatives. But how you are doing, which method you are applying, that you have to specify. Are you getting my point? So you have to mention that the bandpass filter may be the analog bandpass filter may be converted into a digital filter by backward difference derivative method. Okay. So under this condition, we transform S to 1 minus Z inverse divided by T. After putting that, then you will start with the numerical. Okay. So over here, if you look, we have given convert an analog bandpass filter to a digital filter. Here, our HS is given by 1 by S plus 0.1 whole square plus 5 for, and it is given capital T is equal to 0.1 second. Again, if I do not give this, you have to assume T is equal to 1 second. Okay. Now it is very simple. 1 minus Z inverse divided by T. This S is being changed with this one. 1 minus Z inverse divided by 0.1 plus of 0.1 whole square plus 5. Okay. And then you solve these equations and you get to the equation. You need to further solve this equation. Okay. So with this we complete today's lecture. I will not start the next topic today. In the next class we will start the next topic. So if you have any questions, we can take up some questions.
Sir, hello.
In
frequency transformation method, while calculating alpha for the sine and cos value, we will have to calculate in radian mode.
Yeah. Everything is in radians. Whenever you are dealing with any filter questions, it's better. You will be getting most of the things in radians, basically. And
Okay,
if suppose your analog frequency it is given in hertz, it's advisable to convert it into this thing, radians first, and then you start working on that.
Okay, sir.
Anything else? No? Okay, then we'll stop for today.